Now that we've taken those interludes, let's go look at question number 7. Problem set number 4, question number 7. Here we're asking whether or not the long-term historical mean is equal to 211. So this kind of question requires a hypothesis test to answer. If we remember, hypothesis tests have a few formal steps with them. The first step is identifying the null hypothesis. And even that first step, identifying the null hypothesis, has 3 components. The first component is knowing what data it is that we're talking about. And so we are specifically talking about the historical mean. So we just want the historical part, not the future, the predicted. So that's part 1. Part 2 is asking what statistic we are dealing with. In this class, generally, we only deal with the mean. So we don't know how to do tests for medians. We don't know how to do tests for variances. We're really often limited to the mean. So that will be our statistic of choice here. We're asking a question about the historical mean. And lastly, we need an inequality. So we're doing a test. What direction or directions are we concerned about? In this particular question, we're asking whether or not the historical mean is equal to a certain value, 211, the 2030 value. So our inequality is equal. Those are really the 3 steps that we need to know. Part of identifying the null hypothesis, and specifically with that inequality bit, is identifying how many tails your test should have. So if we're testing an equals, so is the long-term mean equal to 211? The alternative to being equal is it could be less than, or it could be greater than. Now, it can't be both at the same time, but it could be either of those, and we don't really care which it is, just as long as it's not equal. When it comes time to looking at this curve and evaluating probabilities, since it could be less than, we need to calculate a probability. And since it could be greater than, we have to calculate another probability. So this will be a 2-tailed test. That may be the easiest way to remember it. Another potential one that I just thought of is if you look at an equal sign, there are 2 lines in an equal sign. So perhaps you color in both sides. I guess greater than and less than signs are also made of 2 lines, so perhaps that's not a good approach. In any case, if you're looking for if something is equal to something, that is a 2-tailed test because it could be less or it could be greater. And we have to account for the probability of either of those happening. Always a good idea to go create a little sketch. In fact, I think question number 7 requires a little sketch. So let's pretend this is my distribution and that it's nice and symmetrical. When drawing your diagrams, there is no functional difference between whether or not your data are normally distributed or t-distributed. They're both unimodal, they're both symmetrical, and I'm certainly not a good enough artist to draw specific t-distributions. So as long as your mean ends up in the middle, then that's good enough. The mean that goes in the middle is not the sample mean. The mean that goes in the middle is the population mean. This is what we're testing. This is our 211, so it's what goes in the middle. And by doing that, we're saying, yeah, we have a sample of 167. So let's go put in our x bar equals 167. This is what we actually saw. It's what comes out of the data. So somewhere over here, we would put a line for 167. And this distribution represents that if we had gone out and taken another sample, then it would be probably not 167. It would be something else. And then we could put that line in the curve. And if we kept taking samples and kind of made a histogram of what those samples' means were, that histogram would look kind of like this. And so we are testing the assumption that if we were to have been able to collect a whole bunch of sample data and plot their means, that histogram would be symmetrical and that the middle of the histogram would be 211. So that is our assumption. Formally, that is what the null hypothesis is testing. If we were to have gotten our distribution and sample means, the mean of that distribution of means would be 211. Our one sample is 167, so we will base the rest of these calculations on the probability, the likelihood that the long-term population mean, historical mean, is 211, given that we observed a mean of 167. So we can flip that around, saying if we observed a mean of 167, what is the probability that the historical mean is actually 211? Either way you want to think about it, we stick the population mean in the middle, and then we calculate some values around it. So we said this is going to be a two-tailed test. So we are interested in some probability over here and some probability over here. From a mechanistic standpoint, and if we remember the interlude lectures previously, we had our two regions, and we knew that there was a line that we draw in between our highlighted and not highlighted regions. These lines were the critical values. Often I've been putting a minus sign in there, but the magnitude of the critical values are the same. For consistency, we'll just put that up there. The area in this curve, this is defined by the confidence level. This was given to us in question number 7 as 90%. So this part of the t distribution makes up 90%, or 90% of the sample means are this close to 211. The critical value differentiates this region from the green regions. And so the green regions here are our rejection regions. And the way this hypothesis test will work is if our sample mean, after it's converted into the correct units, if that sample mean ends up being over here somewhere, or over here somewhere, but within this purple place, then there's a high enough probability of observing that sample mean to be comfortable saying, sure, the long-term mean could have been 211. Our observation is consistent with the null hypothesis, with the idea that the long-term mean is 211. So again, that's if our observation falls in kind of this purple region. If, on the other hand, our observation falls into the rejection region, then we will, imagine this, reject the null hypothesis. And we'll say that, nope, there is too small of a probability to observe what we actually observed, given an assumption that our population mean is 211. Which means we're going to reject that assumption. We're assuming 211. Our data does not conform with that. It's too unlikely to see what we saw. So we're going to reject the assumption. We'll say our assumption is not correct. The long-term mean is probably not 211. So the rest of the step is just defining where our sample mean goes and comparing that to the critical value. We can calculate a p-value and see, well, just how likely is it to get what we got under this assumption. And if that's a small number, then we reject it. And lastly, because and only because this is a two-tailed test of the mean, we can also use a confidence interval and see whether or not 211 falls within our confidence interval. Let's stop there, and then we'll go into calculating the numbers for question 7.